Now we're going to look at a trick which we can actually use to find the dual of a norm. So we've already seen the inequalities for the norm. For example, the inequality was, this is the inequality which we have. Now modulus of y transpose x is less than or equal to f of x into f d of y. Where if of x is the prenorm and f d of y is the dual of the dual norm. So the what we're trying to what we will do to find so basically to find a dual we have to solve the optimization problem, right? What is the optimization problem which we have to solve? The optimization problem which we have to solve is a max of f of x is equal to 1 y transpose x is modulus of y transpose x is the optimization problem which we have to solve to find the dual. But what we can do is, the trick here is, if there exists a theta such that modulus of y transpose z, let's call this x, is less than or equal to theta, okay, for all x such that f of x is equal to 1. Okay, what we mean is y transpose x has an upper bound, sigma. So that is the maximum value it can take. Then if we can find an x dash such that this y transpose x is equal to theta, then theta is the dual norm. We're trying to find, because we're trying to find a maximum. We fix x because x is actually has to follow this constraint that f of x is equal to 1. If that constraint is followed, then if you can find modulus of y transpose x is less than some theta, as n equal to some theta, and we can find a condition where it is equal to theta, which is actually equal to the upper bound, then that we can use to determine the dual of a function. So let's look at this idea and try to find some of the dual norms. So we have a question here. Yeah, see, we have y transpose. In the previous lecture, we proved that y transpose x is less than or equal to y infinity. I mean, infinity norm of y and L1 norm of x, infinity norm of y and L1 norm of x. So can we use this to prove that? Okay, can we use a similar sort of relation? Because how we have derived this, we've already seen. Can we use something similar to prove that the dual of L1 norm is infinity norm? Okay, how did we prove this? We started by saying that y transpose x is less than or equal to is equal to modulus of sigma I is equal to 1 to n yi xi. This is how we started, which is less than or equal to sum of the moduluses, modulus of y1 x1, which indeed is less than or equal to max of 1 less than or equal to I less than or equal to n, modulus of yi, the sigma j is equal to 1 to n, x modulus of xj. Okay, here we have some inequalities, but we have to see where the equality condition hold. Okay, so the question which we have to ask is, the question is, given y, when will equality hold? So we are given y. We are asked when will this equality hold, where suppose x is such that the L1 norm of x is equal to 1. So what we're trying to do is we are trying to find the dual norm of L1 norm, because that's how we are constraining it, right? See, when will this, so we already want L1 norm to be equal to 1, okay? Yeah. So let's first look at a case where this equality holds, right? First of all, for a given x, so for a given y, for this equality to hold, um, x and y has to be positive numbers. What is one condition? Because modulus of of a summation, if it's equal to sum of the modulus, if all the numbers are positive, right? Next condition is we're taking out the maximum, and uh, we are actually summing it all over xj, for the entire xj. So given y, the max of y is also fixed. But when will it have, both of them will be equal? If the xi which we have is corresponding to the I which has the maximum y. For all other cases, if it's 0, then this equality will hold. Okay, so when xi is equal to 1 for, in fact, it's actually need not be 1, it can be non-zero. Uh, for I is equal to argmax I less than equal to k less than equal to 1, y of k, and 0 elsewhere. Right? It has to be non-zero for this case, and for all the other cases it has to be 0. But we have already set the constraint that xi is equal to uh, 1. In that norm for L norm of xi is equal to 1. Then I think also has to hold this condition xi is equal to 1. In that case, is equality holds, right? So what we have on the right side is norm of y transpose xi is actually equal to 1. So this will be L1 norm of y given. Why is it so? What we had on the left side is y transpose x, right? Yeah, let's look at the right side anyway. Right side is max of norm of x is x, no, x L1 norm is equal to 1 modulus of y transpose x. But what is the value of y transpose x? Y transpose x is, this is the max. Xi is equal to 1, norm of x. Y transpose x will be equal to max of am I true? Am I correct? Because x will only have a non-zero value for that particular index, that is k. I is the argmax k. And what is this? This is actually This is the infinity norm. Y x is equal to, so x we already know what this is, like a one hot vector what we have for x. Um, but we have to also look at the left side. Left side is, yeah, left side is y is this norm of one y1 dual, because see, this is the x1 norm is taken as L1 norm, like a norm of x is taken as L1 norm, and so we are looking from the left side. So by the definition of dual norms, that's how it is. F of x is equal to 1. This is actually the dual norm of L1 norm. So this shows that y1 dual of L1 norm is okay. Now let's look at another question given. X, when will equality hold? So x is actually corresponding to the L1 norm, right? And suppose y is such that infinity norm of y is equal to 1. When will this hold? You also again have to look back at this. This will hold. Xi is already given to us. We want this equality, so both has to be positive. Now, for this equality to hold, if y1 is same uh, for all xi's, no, let's take this case, yi is equal to xi by for all I such that xi not equal to 0 and 0 otherwise. What does this mean? Max of this is same as max of my infinity is equal to 1. Right? This in fact this is it is actually x. What is this max of xi? Where do we have this sigma? This is true, but did we miss out on something? We don't have to look at max. Right. Start from here. I'm not really sure what this is done. Sure, sorry. Anyways, okay, let's look at this later. I'm not really sure about this. Okay, but we can also look at at a similar sort of derivation for L2 norm. L2 norm, we have to use Cauchy-Schwarz. By Cauchy-Schwarz, we have uh, modulus of y transpose x is less than or equal to L2 norm of y into L2 norm of x. With equality holding, if and only if x is dependent on y. So if y not equal to 0, then if x is equal to y divided by norm L2 norm of y, it satisfies the condition norm of y takes 2 is equal to 1. So max of is equal to max of this is actually what does this mean? This means that dual of L2 norm is L2 norm, which implies L2 norm is a self-dual. I'm not really sure about this step. This is what we've had. We can discuss more on this in the next lecture.